Okay, so this is similar to the problem that we looked at in the previous video. We want to find the line integral of f over c, but now c is the circle of radius 1 in the xz plane with counterclockwise orientation when viewed from the positive y-axis. So in other words, if this is the xz plane, this would be the circle, okay? And the y-axis is coming out of the screen. The positive y-axis is coming out of the screen, and so we have counterclockwise orientation like this. Okay, and again, we're going to use Stokes theorem. So Stokes theorem says that this integral is equal to the surface integral over S of the curl of f. Okay, and just from the definition of what the surface integral of a vector field is, this is equal to the surface integral of the gradient, or the curl of f dotted with the normal vector ds. And now this is the surface integral of a scalar field. Okay, so now this is the integral. All right, so now let's think about what n is. So well, actually, before we do that, we need to figure out what the surface is. Hopefully you already figured that out, but if not, that's fine. The surface is going to be the disk of radius 1 centered at the xz plane, centered at the origin of the xz plane. Okay, so what is the normal vector for that surface? Well, if that red line has the orientation that it has, this means that the normal vector has to be equal to j. Okay, because this is just a circle, a disk in the xz plane, and so we know that the normal vector is either going to be plus or minus j, but given that it has counterclockwise orientation when viewed from the positive y-axis, it means that n is equal to j, is equal to positive j. Okay, so now this just becomes the surface integral of x squared plus z squared over the surface. The surface is the disk of radius 1 centered at the origin in the xz plane. Okay, now there are a number of ways to do this. You can look at some of my videos, other videos where I talk about this. I'll talk about it again here. I mean, technically, if we want to do this, we need to come up with a parameterization for this surface. We could say that R of ST is equal to something like S0T, where S and T lie in the parameter domain. S squared plus T squared is less than or equal to 1, or we could do a number of these things. But the idea is when you're just integrating a surface that sort of lies in one of the coordinate planes, it's a lot easier. This is just equal to the integral over the region D, where D is just the disk of radius 1 centered at 0 in the xz plane of x squared plus z squared dA, where dA is the dA of the xz plane. Okay, now you could go through all of the parameterizations and stuff, but just think about what's going on here. This is the surface integral in a surface that's in one of the coordinate planes, where y is equal to 0. So this is just a regular integral. The surface is an integral in the xz plane. Okay, or sorry, I meant to say the surface is a surface in the xz plane. It's just a region in the xz plane. So this is no longer, I mean, it's technically a surface integral, but it's a surface integral in the same way that any integral over any region in the xy plane is equal to is a surface integral. Okay, so now this is a perfect polar coordinates problem. We can say x is equal to r cosine theta, z is equal to r sine theta. So this is the integral theta equals 0 to 2 pi. R equals 0 to 1. X squared plus y squared is r squared. And then we have the r dr d theta. Okay, and that's equal to whatever it's equal to. Okay, but the key thing here, the thing that I want you to sort of have in your minds, really has nothing to do with Stokes theorem, and it's just the fact that when you are looking at an integral over a surface, so let's say you have a surface and you want to do the surface integral of a scalar field, so a function of x, y, z ds, this is just equal to the integral over the parameter domain d f of x, y, z dA whenever S is a region in a coordinate plane. Now, to really understand what I'm saying here, to really understand what I'm saying here, you're going to have to spend some time doing problems. And the more and more problems you do, you'll see what I'm saying here. And also, this scalar field that we're integrating, if it's in a coordinate plane, it means one of those variables is going to be constant. And not even if it's in a coordinate plane, if it's any plane that's parallel to a coordinate plane, one of those variables is going to be constant. Okay, and so really it's only going to be a function of two variables. So again, just do a bunch of these problems and what I'm saying will start to make sense. The bottom line is just understand different ways to compute surface integrals.